So hello everyone, I'm Madeline, this is Sam, we're co-captains on team 417 Skid, and this is Dr. Fraser, he's a coach on team 6220, and we're from Woodinville, Washington. So this summer, or since last year, the three of us have characterized FTC legal motors. So the origin of this project was actually Bob Atkinson, so right, that gentleman over there. Bob Atkinson is an FTC framework software engineer, and you might have heard of his name. He was the Volunteer of the Year last year. So anyways, going back to the Dynamometer, or Characterizing FTC Legal Motors project, the published properties of the motors were incomplete, so the purpose of this project was to provide motor parameters for PID algorithms. Now, there are a lot of benefits to first in terms of this project. One, robots will drive better. So, and we will gain knowledge of the variability of motors and knowledge about the relative performance of different types of motors. And what I mean by this is that this project will allow teams to make more informed decisions when designing robots and choosing their motors. And because we used rev expansion hubs in this project, we uncovered a lot of firmware and hardware, or a few firmware and hardware issues with rev expansion hubs. Oh, now Sam will explain the physics of DC motors.
Thanks, Madeline. Okay, in order to understand some of what we're talking about with this project, you probably have to understand the physics of motors. So here's a brief rundown. Okay, a motor includes a stator, armature, and a commutator. Those are the three main components. A stator, oh, I don't have, can you see it on here? Shoot. A stator is the two blue magnets, as you can see there. They're stationary magnets, which create a constant magnetic field. The armature, oh, thanks. The armature, which you can see here, is made of coils of wire, which induce a magnetic field and torque as current flows through them. And then this is a commutator, and it connects the armature to a DC power supply. Motors are a way to transform electrical energy into mechanical energy, and this works as the DC power supply is connected to the commutator, which then makes current flow in the right way as the armature is turning. And these are all the parameters that we were characterizing throughout this project. The first one, moment of inertia of the armature J. This describes how much the armature resists the change in angular acceleration. B, the viscous friction constant, describes the drag caused by the grease in the motors. And KE, the electromotive force constant, represents the relationship between the motor's back EMF and its speed, or angular velocity. KT, the torque constant, represents the relationship, it describes how much torque you are given when you, with a given amount of current. And R, electrical resistance, is the resistance of the armature windings in the motor whenever the motor is at rest. And L, electrical inductance, is generated by an induced magnetic field. And it describes how much the motor opposes a change in current. Okay. So these are the equations that govern the behavior of motors. The first equation explains how generated torque and applied current are connected with the K value, and then it's this torque applied here and the current through here. Equation 3 is an expansion of equation 1, and it relates the applied current to the mechanical behavior of the motor and the acceleration. It relates the current to the mechanical behavior of the motor, and the fourth equation does the same thing for the electrical behavior of the motor. Now, here's Madeline.
So for each of these parameters, we wanted to make as many accurate measurements as possible. And on top of that, we wanted to make them repeatable. So or more accessible, the results more accessible. So we used a lot of FTC hardware and FTC software. So for example, we used Rev expansion hubs, which are legal in FTC. We used FTC legal robot controller and driver station phones. And we also used quite a bit of Actobotics. If you look at our dynamometer over there, all of the base is made of Actobotics parts. And we used sensors such as the Adafruit INA 219 current sensor, and we have two DC power supplies. We built an electrical filter, and we used an LCR meter and a digital oscilloscope. Now, the power supplies and the electrical filter and the LCR meter and the digital oscilloscope are not FTC legal, but as the project grew more complicated, we had to use them. So for each parameter, we calculated each parameter with different experiments. So first, to determine K, first I would like to note that KT and KE theoretically have the same value. So the difference is we have to find KT with acceleration, and this is dependent on the gearbox drag. And now, we believe that the reason for the lack of equivalence in KT and our KE measurements in our experiments is because we measure the torque after it's through the gearbox. And another thing to mention is there's a direct way to measure KT and an indirect way to measure KT. So the direct way to measure KT is to measure the reaction force with the lever arm. That lever arm is attached to the cradle of the motor, and then it rests on the scale, and then and then the indirect way uses angular acceleration. And to calculate L and R, we just used an LCR meter. So since resistance and the inductance values depends on the position of the commutators, we turned the motor shaft to random positions and then recorded the L and R values. We did this 10 times, so we did 10 random positions and 10 different values for L and R, and then we averaged each of those. And we couldn't do this experiment simultaneously with other tests, although that would have been more efficient, or simultaneously involving other tests with rotating motors, because the LCR meter won't operate when the motor is generating its own voltages. So we just turn it to a random position, and it's not moving, and then we measure the L and R. And then next, J is measured with a digital oscilloscope. And so what we do here is we set up the motor with no load on it, and then we set the oscilloscope to single trigger mode, so that when you turn the motor on, it triggers on the first encoder count. And then we let it capture encoder counts versus time, and this motor starts at rest. So this is our fastest measurement, and so for each test, we only take a very brief sample. So the test overall is only a fraction of a second, and there's no significant speed in the motor yet. And last but not least, we have B. So for this test, we give a constant current to the motor, and then we let it reach its maximum velocity so that the acceleration is 0. And then we use known values. To reduce this data, we use known values of KE, but because we don't trust the values for KT very much, and we will get into this more later, but J and B should be close enough, because J and B aren't that significant in terms of tuning PID algorithms.
Okay, this is a block diagram describing all the components of our dynamometer. This is the motor. It's not to scale, in case you're wondering. This is the motor, and as it spins, it applies a reaction torque to the scale. And then this is our 25-to-1 gearbox, which allows us to use a smaller moment of inertia than would have been necessary. And this is our flywheel, which acts as our moment of inertia. And this is an electrical diagram of all the electrical components on our dynamometer. When the relay is on, the power goes through the relay and the filter and the sensor to the motor. Okay. In order to get accurate and repeatable results, our dynamometer had to meet certain requirements, and this is what it had to do. It had to be able to measure torque, and it had to have a large moment of inertia. It had to have a controlled current source and a digitally controlled power switch, and we had to be able to monitor current and voltage, and we had to be able to count encoder counts. Okay. Oh. We were able to measure the torque with our 25 centimeter lever arm and scale, as we described earlier, and we had to use a gearbox in order to reduce the size of the motor, reduce the size of the moment of inertia. The moment of inertia felt by the motor is the gearbox ratio squared multiplied by the original moment of inertia. For our controlled current source, we used a DC power supply, and for our computer control switch, we used a relay. The relay allows the rev hub and phone to have control over when the power is on or off. And then we monitored voltage and current with a Adafruit INA 219 sensor. Originally, this sensor only had a range of 3.3 amps, but we wanted it to have a range of 16 amps. We changed the resistor on there to a 0.02 ohm resistor instead. And then we had two methods of encoder count logging. We had a digital method using the software that Madeline wrote, but this was limited to a max of one sample every 30 milliseconds. And we used this specific, and then the oscilloscope method could acquire samples much faster, but it couldn't conveniently take a large number of samples.
So before we could collect any data, we had to manufacture many parts on our dynamometer, which we have listed here. So these are all of the parts, and I will get into that. So first we have the flywheel. The picture on the left shows the flywheel mounted on the dynamometer, and so this flywheel has a bearing mount here, it has a coupler, it also has a coupler on the other side, and there's a motor mounting plate to drive it from the backside. Fun fact, it weighs 7 kilograms, and if you can look right here, there's a small dimple on the flywheel. There's also a dimple on the other side, so the flywheel is perfectly balanced, so that when it spins really fast, it's still safe to use. And then this over here is the flywheel axle that we made on a lathe, and it fits inside the flywheel with 2 10,000ths inch of a taper. So yeah. And then next we have the gearbox. We used brass pinions running on aluminum gears for lower friction, and it's better wear resistance as well. And then over here we have a jack shaft. Oh, and this gearbox is a 5-to-1 and then a 5-to-1 gearbox, so overall that's a 25-to-1. And about the plates, we clamped them together while we were drilling the holes for the bearings so that these holes line up really nicely. So they line up with a tolerance of 2 thousandths of an inch. This is, these are our standoffs. There are actually 4 of them. And so there are 2 holding up the flywheel and 2 holding up the motor cradle. And there's, yeah. And then this over here is Sam starting an axle to match the taper on the flywheel. She used a micrometer to measure the taper and the diameter. And then here's a few pictures of us at work. It was a lot of fun. We learned how to use the lathe and the milling machine. It was a very rewarding experience.
Okay, this is a picture of all the components of our dynamometer. Here are the power supplies, and this is our filter that we had to build. This is our flywheel, and this is our gearbox and our motor cradle. We had to have a separate setup for this motor because it's shaped weird. And this is our lever arm and our scale, and this is our digital oscilloscope and LCR meter. Oh, back to you.
So for some of the measurements, specifically the K measurement, we had to write our own software. So this is a list of our data logging software. And so the first data logging software test records time, encoder counts, shunt current, and bus voltage every time the encoder count changes. And then another version of this test records those 4 data samples every time, or about every 30 milliseconds. And this data is written into an array. And what I mean by this is each time is stored in its own time array, encoder count's stored in its own encoder count array, and so on. And then at the end, after we have done all of our data sampling for that test, this data is stored into a text file, and which can be accessed from the RC phone, and then put into a spreadsheet for further data analysis. And then we have one debugging software test. That was just the encoder count test. It's just really simple software that displays the encoder count in the driver station phone's telemetry while the motor is turned off. So somebody must manually spin the flywheel. And we created it because we thought we were losing encoder counts for one test, and the calculations for that test didn't make sense.
Thank you. Throughout our project, we encountered many complications, as you can see here. And we had an encoder bug in which we, as Madeline mentioned, we were losing encoder counts, about close to a third of them, and our results were not repeatable. We realized that the rev hubs two of them were software counted and 2 of them were hardware counted. And the hardware counted we were using because it allows for much faster counting. But this was not filtered the same way as the software ports, and thus it was subject to a lot of noise, and that's why our results were very different. We also had a few problems with the rev hub cables. Specifically, they had no strain relief, and they would break off at a connector point, which was very difficult to repair. And so Samantha Schatz came up with the idea to use a heat shrink cable, which gave us a good grip, and we definitely recommend that to anyone who's having trouble with these cables. Also, as we were trying to measure our K values with different experiments, they weren't matching up because we would get different KT measurements than KE because the KT is measured with a torque, and the gearboxes of the motors are variable and not precisely accurate, not completely efficient, and thus the B and omega term doesn't accurately represent the drag, especially at low speeds. We also encountered a lot of noise with our bus voltage data. As you can see here with the blue data is the raw data that we received, and we tried to filter this by averaging the data, and that's the red, but still that wasn't quite enough, and it was still very noisy, and we couldn't get any accurate results from it. So we realized that we couldn't digitally filter it, we had to physically filter it. So we built a low-pass filter, which allowed only signals under the range of 15 hertz to pass, and the noise was caused by the commutators in the motors, and that noise is around the range of 100 hertz, so none of those signals would come through with this filter.
So now I'm going to walk through how we reduced some of our data collection in our experiments. So first we have the Flywheel and INA Experiment, and this experiment is used to calculate K, or KE more specifically. So this is example data from the AndyMark 40A motor, and on the first graph we have actual position versus fitted position, and we calculated the fitted position using Solver on Microsoft Excel. And so for the test, we applied power to the motor for 30 seconds, and then we shut power off and continued to collect data for another 30 seconds. So this is data of the motor accelerating for 30 seconds. And as you can see, it fits very nicely. And then the second graph, the x-axis is velocity and the y-axis is bus voltage. So we basically graphed bus voltage versus velocity after the current was shut off. So this was after 30 seconds. So and then the slope of this line is KE. So, all right, next we have the free motor spin-up experiments, and for this, we fit actual position versus fitted position, just like in the K calculation. And so the second equation here is actually that fit equation, and that's shown on the red graph. And over here, K times I is from equation 1, if you go back to the equation slide, and then J times A, or alpha, is is equation 3, and it's simple. And this is simplified to ignore the B term because velocity was small enough to be negligible. And in the second equation, P0 represents an arbitrary starting position, and then T0 represents an arbitrary starting time. We don't measure either of these, but we do find these values when we are just looking at the oscilloscope data. And then if you look a little closely at the graph, you're going to see a little squiggle right here in the actual position. So that squiggle in the graph is actually an artifact of the oscilloscope switching scales. And next we have the LCR experiments, and like I said before, we measured L and R using the LCR meter. So another thing we measured was DC resistance at each random position in DCR mode, and we use this as a check for the resistance calculation, which can be calculated with this equation over here. And the average values of L and R are at the bottom of this table. So we recorded each L and R at each random position, and then we averaged them.
So these are the summary of the results of all of our electrical experiments. This shows the average of each motor. We tested each type of motor 3 times and then took an average of the results. And we believe that the R value is is a lot less accurate because it's measured at 1,000 hertz, and motors are not designed to operate at that frequency. And this is the summary of our hardware experiment results. As you can see, the KE values are very accurate, and they also represent the trend of the gearbox getting large, the gearbox values. So the KE for AM20 is smaller than the KE for the AM40 and for the 60. And we believe this percent error is because we used one AM40 motor to do all of our original tests as we were figuring out how to do our experiments, and that led to a lot of the grease getting squished out and had a different viscous friction constant.
To summarize this project, we started by researching equations of each of the motor parameters, and then we designed and built our dynamometer to measure these parameters, specifically for FTC motors. And then we measured the motors and then reduced the data, and we also prepared a report on characterizing FTC motors. Now on this report are procedures for each of the tests and just overall information about manufacturing parts. All the records are on there. So, and this project was a full-time job over the summer and part-time during the school year for us 2 interns. Oh, and here are some pictures of us at work. So here's the initial brainstorming process. We just brainstormed on the whiteboard and ordered activotics pieces. It's quite a lot of fun. And then, this was actually getting ready for Andy from Andy Mark. We showed him the dynamometer. He loved it. It was a great time. And here's us. Learning how to solder. We put together the INA 219 sensor there. And here's us making the relay. And here's us reducing data. And here's us machining. Okay, so the next steps to this project is to measure Andy Mark orbital 20 motors and the Pittsco Tornado motors. And after that, we also have to further investigate the gearbox effects on KT, J, and B because we're still not really sure about those parameters. And then we might also want to measure other parameters that more specifically other FTC people as a majority are interested in. So are there any parameters that you guys would like to know about? Or
It's probably a question to think about.
yeah, something to think about. There you go. And we would like to thank Bob Atkinson for our sponsorship. So shout out to Bob. And AnyMark and Pittsco for providing a few motors to test. And we also had a few discounts from from Server City on Activotics hardware. And Brian Willman for many kindnesses. And the complete report will be available on our club website at swerverobotics.org. Oh,
That's just for
yeah.
questions. Questions? Oh, yay! Yes?
Yeah.
Oh, nope. I'm not quite sure how much it costs. We didn't personally worry about that. No, I just meant, it was, okay. We weren't always there while we were purchasing parts, but it was a full-time job over summer, 8 hours a day, and most of the time, especially during the summer, was spent machining parts and learning how to mill and lathe.
And then it was part-time over the school year, so I would say about 3 to 4 hours a week. So, yeah.
Yes?
So have you had a chance to go back and now look at your data as it reflects, do you know if it reflects well on the specs on motors? Meaning, do you find any surprises, I guess, is what I'm asking.
Well, the AM60 motors tended to act wildly differently from each other. One of the motors we couldn't actually test because it ran completely differently, and as the motor runs for a long period of time, its behavior oscillates because of the grease in the gearbox. The grease is, the drag changes based on the temperature, and it just acts very oddly, and the 60 motors are just not rather inconsistent with each other. That's what we found. Yes?
So,
Oh.
want me to answer that one?
Yeah, that sounds good.
We did not do a systematic stepping the current and looking at the torque to see if K was exactly independent, but we did measure some motors at multiple currents, and it did tie together very nicely, yes. Yeah, there's no underlying physical reason why it wouldn't be that way unless you turned the current way up and the motor got hot. We never ran our motors long enough to get them hot, except for the AM60s, and it was really the gearbox that's getting hot that was interesting in those. It's, yeah, for low speeds it is, for current, and for high speeds it's not. For voltage it's practically never linear. Yeah, we chose that particular formulation of the equations at the beginning. If you could scroll back there to the
Go to the, yeah.
We chose that formulation of the equations just because it is strictly linear and strictly straightforward. If you start with current and angular velocity as the independent variables, if you start with voltage or torque, then it gets fairly difficult to separate things out to measure the other two variables. And particularly the AnyMark 60 was fun doing basically the terminal velocity test where you just apply a current to it and wait for it to come to a constant speed. It never comes to a constant speed. It oscillates up and down in about a 3-minute period. And just because the gearbox gets hot and the drag goes down, it goes faster, the gearbox starts to cool off and it goes back up again.
What's your question? I actually am not knowledgeable at all on FRC motors, so I wouldn't know. But realistically,
It depends on what we're testing.
realistically, we would just have to,
I think you need a bigger dynamometer.
yeah, overall
So
bigger.
you can come up and look at this hardware, try to spin that flywheel, at 7 kilograms.
You can see
quite
that
fun.
it's also perfectly
And with
balanced.
a 25-to-1 gearbox. If we didn't have the gearbox, we would have been using a manhole cover for a moment of inertia. So if you want to do this with an FRC motor, you probably need a Ferris wheel.
Yep. Yes?
Difference between motors is always an issue. So, and something you said earlier was the specifications you get for motors are inconsistent. They're all different. It'd be really amazing to see a set of graphs produced from your data, so we had a consistent motor curve for the various motors.
So,
Yeah, then how many motors would you like
Yeah.
to buy for us to do that experiment?
No, more like, but I would assume, based on the numbers you collected
Yeah.
and the equations that are there, you should just be able to create a curve for it. Is that not true?
well,
So
we only
tested
took
3 motors of each type, and for KE, they were quite consistent with each other. And for L and R, well, L was quite
Okay,
consistent.
yeah.
R was pretty consistent. The J's were fairly good, and the B's were not.
I think you misinterpreted my question.
Okay.
I said different motors, I
Mhm.
mean different brands of motors.
Oh, different brands of motors. So these parameters are all design dependent. So for different designs of motors, there's not really much way to tie them together. You're probably thinking of more the parameters that we didn't test than the ones we did. You know, like stall torque and maximum speed.
So they can't be.
We could test them. We
No, I
didn't.
mean derived from the numbers we have. We can't.
Yeah, and in fact, some of them can be derived from the data we have.
Right.
But, for example, we did all of our measurements at constant current. You typically want to know what's happening at constant voltage. It happens that our logger was logging the voltage all the time it was logging the torque. And so we could go back and look at the voltage as a function of speed. You can also calculate it from these numbers using these equations, but we have not done that. But sure, somebody could look at our report and go do that.
Yeah.
And they
All
would
of our-
happily put it on our website.
all of our data will be included in the report, so you can draw any conclusions that you would like from it. Yes?
So I know you guys have worked on how to take it through coefficient balance and correct the functions to get. But is there any plan to do that? Or
Stay tuned. Yeah, more students will do more things. Well, one of them is graduating.
I'm graduating.
Yeah, that's a really good question. I
Um,
mean, the whole reason for doing this was just so that could be done.
If any of you want to look at our
Yeah, come
project
on
that we
up, we'll
built,
fire it
it's
up for you.
pretty
Welcome to
darn
look.
pretty,
Yeah.
I would say. And there's a lot of really well machined parts that I'm very proud of. So,
Yeah,
Somebody
if
wants
you
to look.
ooh and ah about the axle on the flywheel, they'll get really jazzed.
oh, wait. A fun tip: the axle in the flywheel is tapered to 1/2 of an inch, and I did that.
Come on up.
Should
It's
we
not going to
go
bite you unless you stick your finger in
I
the
mean,
gears.
if you would like to, absolutely.
Try to keep the flywheel below 2,000 RPM.